Wonderful. All right, let's dive in. I'll put the contact details up again towards the end so that you still have them. And I'm going to quickly set a timer to make sure I don't run out of it. Brief bit of housekeeping, questions. The Q&A panel, I know somebody was asking, is it working? If it is working, then feel absolutely free to put questions in there as I go through the talk. I'm going to ignore them until I get to the end because I'm a little nervous that I'll just get distracted by all the questions and want to respond to them right away. So I'm going to try and get to the end with time to respond to them. There's a little thumbs up icon as well I've noticed throughout the day. So if you click that to say you would like an answer to that question as well, if there's a bunch of them at the end, I'll pick out the ones that have the most thumbs up and come to those. Quick overview of everything I'm going to try and get through in the next 40 minutes. First, I'm going to speak very briefly to the research base and where these ideas are coming from in the first place. I want to touch on this idea of understanding, because when I've tried to articulate this idea to people in the past, a blocker that I've often encountered is the belief or the fear that this is an approach that runs against developing understanding or would prevent mathematical understanding. And I think the absolute converse is true. I think if we want to get there, this is how we've got to do it. So I want to dive just a little bit into the idea of understanding what it looks like and what we need to do to develop it in order to try to head off that objection at the pass, if I can. And then I'm going to go through a single concrete example of something that I used to do in the classroom, followed by what it is I do now, so we can see the difference between the two approaches, followed by an explanation of why I do it this way. And once I've gone through that, I'll go through a second concrete example for comparison. And that's what I'm calling sort of part one of the presentation. Part two, just a little bit of commentary, because there's quite a lot going on beneath the surface with this, and I'm not going to get to cover all of it now, but I think I can do a little bit of it some justice, including why I didn't do this right from the start, what it was that helped me overcome that, a little bit about what this approach isn't, which I think will be important, and then finally what its limitations are, so what's still missing, rather than trying to pretend that this is covering everything. Okay, so the research base to kick it off. What I would say this is an approach based on research-informed, evidence-informed theory that I've read about, I've interpreted, I've then tried things out in the classroom. And so the second thing it's based on is my own experiences of how this has worked. So we've got research-informed theory followed by my interpretation of that and experience. What it's not in terms of the research base, I'm setting up quite a clear two-trial system here. You've got one case where effectively you put the why before the what, you derive from first principles the processes or the ideas you'd like students to grasp. And the alternative is you swap that around. You go straight into the what, explain how to do it, and then you come back to explain why it works later. You could, in theory, pit those two against each other in a randomized control trial. Insofar as I'm aware, nobody has done that. If anyone who's in the webinar knows differently, then feel free to put that in the chat and I'll see it later and I'll be diving into that research if it exists. And I certainly haven't done that research. So it's not like these two have been tried against each other with tens of thousands of students and we've seen which came on top. It's more, there's an evidence base that is underpinning it, that serves as a foundation. And then my own experience has given me the confidence to go with this. And I suppose this is in some ways an act of persuasion. I'd like to persuade you that this is worth trying. I'd like to persuade you that there's a good argument for it, that it will lead to good things ultimately. And if I can persuade you of that, and if you do then go on to try it in your own classrooms, hopefully you will see the benefits of it for yourself. So that's all I'm going to say on the research base for now. I'll talk a little bit more about what that theory is and where it's come from as I go through. So next up, understanding. Probably throughout the day, depending on which workshops you've been in, you will have seen a diagram that looks a little bit like this. It is one way of thinking about what we mean by a mental schema. The idea of acquiring knowledge represented by the circles, the nodes in this network. Typically, I think it would be conceptual in almost every case, but that's a deeper conversation. And then relationships between the knowledge that you possess. So you've got two major variables here, quantity of knowledge and quantity of relationships between the knowledge. And we can have a situation where you don't have a great deal of knowledge and what you have is not very well interconnected. Or you could know a lot of things, but it could be relatively discrete, not entirely interconnected. I think it was Stuart Walsh this morning said in the first session, said something about students often needing to feel like they need to memorize lots of different processes. So if you don't know all the, if you can't see how everything is connected, then you will just treat everything as a collection of 1,000 discrete things that you need to memorize, and that's truly burdensome. You can have a situation where you don't know a lot, but what you know is deeply connected. And the dream, of course, is to have knowledge that is comprehensive and very well connected. And this is just, I guess, like a representation, like an idea. We don't need to treat it too seriously, but I find it helpful for thinking of understanding in terms of increasing quantity of knowledge and increasing connectivity between the knowledge you have. Some people do take this further. They start giving the lines more properties. The lines can get thicker, or they will say that understanding is just the number of lines in the network rather than attributing it to the number of nodes as well. I think these are sort of nuances that don't serve us too well right now, but suffice it to say, for my purposes, I'm treating increasing understanding as increasing quantity of knowledge and increasing connectivity of the knowledge that you possess, increasing relatedness in that knowledge. And so our goal is obviously this top right quadrant. And if we help ourselves to the assumption that we as teachers are already up in that right-hand quadrant, I don't think that's always true. That has certainly not been true for me for some topics I've taught in the past, and it probably still isn't true for some topics that I would try and teach today. But if we help ourselves to that assumption to begin with, what we're going to do is take a look at that, and we're going to say, this is where I want my kids to be. I want them to know all these things. I want them to see all this beautiful interconnectivity that I see. I want them to appreciate this and be in awe at its grandeur and its beauty. But certainly for me in the beginning, I definitely in the early days, I went in there and I was so anxious about missing bits of this beautiful picture out. And so I would try and teach all of it in one big go. And I felt and I behaved as if that were the only way to do it. And I would say now that that is pretty much guaranteed to lead to some kind of cognitive overload. It is too much information. Instead, you're probably going to succeed in teaching nothing. And instead, what we need to do is teach one thing at a time and build on top of each new thing that we teach. And we have to make a lot of choices there. We have to decide, of all of this, what are we going to teach first? And it is necessarily going to have to be one of the bits of knowledge, one of the sort of concrete concepts that we can grasp onto, or abstract concepts. And then secondly, we're going to have to teach another bit of knowledge. We have no choice. There's nothing to relate yet. But now we have a choice. We could teach another, we could teach the relationship between those two, or we could bring in a new piece of knowledge. We could bring in more knowledge, or we could now start to focus on the relationships between what has already been taught before bringing in more knowledge and then connecting that to the network and so forth. And over time, you're building up the more complex schema that we saw earlier, our ultimate goal. So this is all to say that that is very much my end goal. This picture is very much my end goal, but my way of getting to it is perhaps looks a little bit more like this, piece by piece, building it up, not throwing it all there in one go. And I said I used to think that I had to give it all up in one go. So I want to go through a concrete example of what that looked like for me now. So this is what I used to do to teach children how to simplify numbers in index form. I'd start with one example. I plucked this one out of nowhere. As an example, I could have started with this. And then I would I'd probably present something up front, something to make the point that there is a simpler way of expressing this, and that this is what I want to show them. So first of all, I could make the point that 7 to the power of 10 is, of course, equal to 7 times 7 times 7, 10 times. And again, I'm assuming that this is something we have already covered before. We've taught them this previously. Oh, I just want to make a point at this moment, actually. I really hate trying to set out mathematical working on PowerPoint. I mean, an absolute nightmare. It takes ages and it never looks the way I would do it on a whiteboard or in a visualizer. So everything I'm presenting here, I would say, I would set it out something like this. This isn't necessarily exactly what I would write on the board, but something like this. So we're going to make the argument that 7 to the power 10, we know, is a shorter, a simpler way of expressing this beefy multiplication on the right-hand side. We can make the same point for 7 cubed, or 7 to the power 3. And now I've got my expression 7 to the 10 times 7 to the 3. And I would do something to show that these 10 sevens relate to the 7 to the 10, and something to show that these 3 sevens relate to the 7 to the 3. And we've got that lone multiplication symbol still, which relates to the multiplication symbol between 7 to the 10 and 7 to the 3. So all in, we've got 10 sevens, and then we've got 3 sevens. So all in, we've got 13 lots of 7 being multiplied by each other. So we can argue 7 to the 10 times 7 to the 3 is equal to 7 to the 13. From there, we can express, therefore, it was actually equal to 7 to the 10 plus 3, or that would be another way of expressing it. That ultimately, in order to simplify this, all we need to do is add the indices. So having gone through all of this, I mean, this is one demonstration. I think in my first weeks, I probably assumed one demonstration was sufficient. I might not anymore, so I might have demonstrated this once. I might demonstrate it again. I would obviously, in reality, use different numbers. Please forgive me, I didn't want to go through and change all of the sevens on that initial slide, but assuming I've used different numbers, I'd go through a similar demonstration again to show that the same result occurs. We again end up with a result which makes sense, and which we could re-express as the addition of those two indices. Probably go through it at least one more time, 2 or 3 times. I might at that point choose to conclude, in general, we could express this as algebraically, a to the m times a to the n is equal to a to the m plus n. So in general, that always works. I would then rush to the internet to find a worksheet that would allow students to practice this. And almost invariably, the worksheet would not practice exactly what I'd demonstrated or what I wanted them to now do. I suppose I eventually gave up on worksheets on the internet and tried writing my own, and that felt burdensome as well. But this is, broadly speaking, what a lot of my teaching looked like, certainly for my first year and on and off for my second year as well. Elements of this actually lingered throughout all my years of teaching. I found that this is very naturally how I wanted to approach everything. And moving away from this was actually tricky. But I did eventually move away from it, and I do it very differently now. And the way that I approach this now is, so what I do now, I again start with something like 7 to the 10 times 7 to the 3, same example I had previously. I would start with a very similar preamble to what I had before, something that tried to impress the desirability of simplifying this, of being able to express it with less writing, less hand cramp while you're in the classroom. That's got to be a good thing, right? But this time, all I would do is say, it's possible to do it. My turn first, and I'm going to show you how to do it. So how can I simplify this expression? Like this. How can I simplify this expression? Like this. How can I simplify this expression? Like this. One important difference, if I were in the classroom, I would probably want to use a whiteboard. You may have spotted, I hope you've spotted, that between first and second and third examples, only one thing changes each time. So between first and second, I changed the base number from 7 to 3. Between second and third example, I changed the number 10 to the number 8. And what I would actually do in a classroom context, I would probably use mini whiteboards for this, almost invariably. I would actually let them watch me rub out the 3s. I'd say something like, I'm going to change just one thing. Let them watch me physically rub out the 7s, replace them with 3s, and then pose myself the question, how does this change what I have on the right-hand side? And then I would let them watch me rub out the 7 and replace it with a 3 on the right-hand side. I'm going to change just one thing again. Rub out the 10, replace it with an 8. How does this change what I have on the right-hand side? Let them watch me rub out the 13 and replace it with an 11. As soon as I've done that, 2 or 3 quick examples, I'd get through that in about 20 seconds. Again, I've now got some initial assessment, again on mini whiteboards. To make it as fail-proof as possible, I would present this to begin with and just ask, your turn, what goes in the box? Actually, one thing I might do before that, this now comes down to a point of teacher judgment. Sometimes I do this, sometimes I don't. There are reasons behind it, but to satisfy the question, because I'm sure it'll come up. At the end of the sequence, usually at the end, not before, I might express in words. Each time, provided the base numbers are the same, I can just add together the indices. So I would verbalize what I hope and what I'm very confident they have already identified for themselves. I've deliberately chosen numbers that make it almost impossible for them to not see what's happened. 10 plus 3 is how you get 13 each time. It's verified by the fact that 8 plus 3 is 11. And now they get a chance to double check that because it's their turn. One number should go in the box. And that's all I'm looking for at this point, like 2 to the 19. Again, I've made it a little easier. One number should go in each box. And I've changed just one thing, the 10 to the 5. And I'm going to get rid of that structure, that scaffold, the boxes. But I am just going to change one thing again. This time, I'm going to write the digit 1 to the left of both of those 2s. So we now got 12 to the 9 times 12 to the 5. And each time I'm asking the question, how does this change what you have on your whiteboard? And this is very fast. This is very, very fast paced for something like this in the classroom, because all they've got to do is boards down, write a 1 in front of the 2, boards back up, and I can very quickly verify for all of them whether they have that correct or not. So the pace of this initial assessment in particular is extremely rapid. I can also start to throw in things, and you've got to picture, I love doing this with, in particular, this next one, I love doing this kind of thing with, I've got in my head, I taught a nurture group in my first year, bottom set, nurture group year 7. I taught a similar group in my second year of teaching, but in my first year, this was a lovely, lovely group of 6 kids. In my second year, this was not a particularly lovely group of 15 kids. But in each case where I did something like this, I was able to throw in something like this next one. And to those kids, this seems like they're doing something difficult. It looks different, it's a big number. In actuality, cognitively, there is very little work to do here. All they are doing cognitively is summing 40 plus 7. And again, it's just verifying that, that they know to do that, even when it looks different and looks a bit weird. But you've got to picture those classes. You must have taught them at some point, and you've got to imagine how much pride they feel in themselves when they feel like they're doing something very difficult. I've seen extraordinary teachers pull off this trick many times. They present something which suddenly seems complex. It looks difficult on the surface, but in reality, you can guarantee that your student will be successful in it. And every time, the amount of pride and success that I've seen is genuinely heartwarming. Warming doesn't really feel like the right word. It's something more intense than that. You feel a great deal of pride on their behalf. And it gets better because this is just what you do to verify that what you originally presented made sense and you've communicated what you needed to. From there, we get into this thing called an expansion sequence. And this is where the real fun kicks off. Because now I'm confident that they know, they know the rule for multiplying numbers in index form. So now we can start playing with this and have some fun. For example, I could present this and ask what goes in the box. Extremely easy to answer. Likelihood of failure is extremely low, and yet it's a question I have not shown them how to answer. They do need to figure out the answer of this for themselves, and that is where that dopamine kick comes from, the sense that they've solved this little micro problem, as I sometimes call them. Marginally trickier, but I'd still have pretty good confidence they could all do this, even picturing my bottom set year 7s. Now, I'm not necessarily convinced they would all deduce that they have to work 20 subtract 11, but I'm pretty confident they would all at least realize I need two numbers that add to make 20 and very quickly recognize that that's going to be 9. Either they would need to have been like pre-taught another lesson, or we'd have to cover it now, the fact that and when you don't see a power, that's always equal to, there's a power 1 there, there's a secret 1 hiding away. So 3 is in fact equal to, or equivalent to 3 to the power 1. So that then we can start bringing in something like this, which, you know, to you and me, again, with our expertise-induced blindness, with our complex understanding of all this stuff, that seems like exactly the same problem I've presented every time so far, but it's not. They have to first realize that that is a secret 1 there. It's not made explicit to them. It's currently covert. They have to themselves, and I'm not making it overt for them. I'm right now not writing the 1. They have to do it for themselves. They have to realize that before they sum the numbers. And that, again, if they succeed in that, they are succeeding in doing something for themselves. And I'm confident that they would succeed in it. Assuming they have, we can now take this further. We can start looking at 3 of these multiplied together. Now, I probably wouldn't. It depends on the class. Start with 2 to the power of 1 because of the secret there. Maybe I'd put a 2 to the power of 3 in there. But again, I haven't shown them how to do this. I haven't shown them how to work this. Depending on the class, you'll get some kids who'll say, I've never seen this. I don't know how to do this. Sir, you haven't taught me how to do this. Miss, you haven't taught me how to do this. Guarantee if you say to them, you're right, you can preempt this quite often as well. You can have a lot of fun with it. I haven't shown you how to do this one. I'm not expecting you to be able to do it, but I think you could probably give it a guess. And if you guess, I think there's a good chance you're going to get it right. So don't worry too much about getting it right, but just give it a guess and see what you think. And you just guarantee that there's nothing else they can guess. They are going to guess 2, and then they're going to add up the indices, and they're going to have it correct, and they're going to have taken that leap for themselves. We can now play this game again of making it look more complex. So I'm going to change one thing. I'm going to change the base number only. I'm going to put on a whiteboard, I would just add the negative symbol in the brackets. I can go further again. I can put a 1 on top of all of those 2s and make it look more complex again. And each time just ask, well, how does this change what you have on your whiteboard? Very fast, doesn't require, it doesn't require lots of time to rework things out on the whiteboard. So we're getting to quite, I mean, all of this can be done in just a few minutes. We can take it further. We can rub everything out and now ask, what about this one? And again, it looks difficult, but by this point, they will have learned the base number always remains the same. They just need to add the indices. Even if they haven't done much work with algebra, they could deduce the same for this point here. The next example is a bit different. It's actually a generative activity. There's an infinity of different options that can go in those 2 boxes. So this is something you could spend a lot of time on. For the kids who map out all of the integer pairs quite quickly, you can challenge them to say, consider what else could go in there. Go get into negatives, fractions, and so forth. You could question, depending on the class and their prior knowledge, is it possible to put 1 or more irrational numbers into those 2 boxes? It's a particularly challenging question. We're back to a non-generative exercise in this case, but again, it looks different. It's a new type of question for them to answer that doesn't require any new knowledge. And if we've got a group, definitely not my year 7s anymore, but my year 8 top set maybe, if I've got a group who know some basic algebra arithmetic, I can start presenting them with expressions like this and ask them to simplify that. And if successful, I can remove that base number and make it even more algebraic. I could take it even a step further, change one thing again, change that M, that second M, to an N. And then I could ultimately remove those coefficients. So I'm just left with this. And again, it depends slightly on the prior knowledge and ability of the group. But if you've got a group of children whose algebraic arithmetic is sufficiently strong, they will, at this point now, deduce for themselves the general form of the index rule. There's a lot missing from this particular sequence. I haven't put anything in there where base numbers are different and looked at when you can't simplify and challenge that. I haven't really included yet negative or decimal or fractional powers, for example. I've kept all the powers very simple to begin with, except for the algebraic expression. So this is just a taste. This is just one tiny example of what could be done with sequences of this type, which can also be built into worksheets. I've talked a lot about using whiteboards, but that's just to make sure that everyone in the group can do this kind of thing. And then you can hand over the worksheets either in the same lesson or in future lessons so that they have more opportunity to practice and explore further. And all of this really is still rooted in a what or a how, what to do in order to simplify, or how to simplify expressions of this kind. I haven't explained why this works, but by the time we've gone through all this, and this might not just be one lesson, I might repeat sequences like these with subtle changes time and again over a number of lessons, maybe a few days at least. Could go longer. We do need to start thinking very strategically and long term, I think, to develop real mathematical understanding. But at some point, I'm going to make a judgment call, and I'm going to say, right, we've hit this point where you're completely fluent in this. You understand how to do this. You're doing it effortlessly. You've completely got it. You're remembering every time. Now I want all of us now to go back to the beginning and start thinking a little bit more again like a mathematician, because up until now, you've just taken my word for it that this works. And I'm very grateful that you've taken my word for it that it works, because if you hadn't, I don't know what we would have done. This would have been carnage. I'm grateful that you've taken my word for it up till now, but it's time. But you shouldn't have to all the time. And now it's time for me to prove to you, to show you how and why this works, and how you can be confident in yourself that this works. And so now, having gone through all this, now we're going to effectively go all the way back to that first slide that I showed you, some version of that, where we are exploring why this idea that you can just add the indices together, provided the base numbers are the same, why it works. Okay, so now that's what I used to do. It's what I do now. Point number 5, why do I do it this way? Why do I insist on doing it this way? I've listed 3 problems. It's probably more than 3, but I've tried grouping them together. I think there's a real, I think it's a landmine. It's a minefield. It's a minefield, a field full of landmines, trying to cover the what before the why before the what, or at the same time as the what. First, if I go back to that original explanation, there are at least it doesn't, this is probably still working, but my headset's telling me I've lost connection. Can I just check? Can you still hear me?
Yeah, can still hear you, Chris. Yeah.
Fantastic, thank you. It does this from time to time, but I thought it would still be working. Okay, so this feels like a fairly straightforward a demonstration. It's not technically a proof because it's not fully generalized, but a proof or demonstration to us. But we already know the outcome. We already know all this stuff. We know how it all works. We've got that well-connected, comprehensive schema in our own heads. But as you break it down, there are lots of different things that we're asking students to hold in their working memory simultaneously as we go through this with them for the very first time. And I just cannot see a world in which that does not result in cognitive overload for the vast majority of students. There'll always be that minority of students. They'll crop up even in some of the middle to lower sets, if you're using sets. There'll always be some students who follow this and make us feel like we've done a good job. But we haven't done a good job unless everybody in the class has really understood it. Everyone who gave us their trust, everyone who lent us their attention. And I do not believe this is, or more precisely, I do believe this is going to lead to cognitive overload for at least some, if not the vast majority of that classroom. Also, it's not clear what I'm teaching right now. There's so much going on. There's so much going on. At what point is this the thing that I originally promised I would give them? A way of simplifying that initial expression. So we have a very poor signal to noise ratio, lots of noise, very little signal getting through. Is very likely to lead to cognitive overload. And because of both of these reasons, I think it's very unlikely to lead to substantive recall in the future. Those are not my 3 problems. That's just problem number 1. Problem number 2 is how I would come back to practice what we had just covered, because I've basically got 2 options. My options were either I have you practice everything that I've just done the way that I've set it out, which again is introducing an awful lot of noise and quite a lot of cognitive overload and quite a significant amount of cognitive load. And additionally, it's probably going to really frustrate most of my students. It certainly did frustrate most of my students, because but in their mind, we're doing this so that we can simplify the expression. And even for the ones where, the instances where it's like, okay, I've got it, I add the indices, I get it. And now I'm asking them to write all of that out. I mean, they're not wrong when they say it's long. It's long, sir. It is long. It's long, and it's kind of pointless right now, because it means that in a given amount of time, I'm only able to ask a 20th, maybe fewer of the questions that I could ask if I just honed in on simplify these expressions and explored everything we could do with that in all of its rich wonder. So my one option is to get them setting out all the work. But if I reject that option, and I do go back to just simplifying the indices, then this is what I found I would do. I've gone through the explanation. I've given in, the kids are right. Let's just practice simplifying now that I've shown you how it works, and I've satisfied my guilty conscience if I don't show it to you. But that's it. I never come back to it. I never ask them again at some point in the future, how do you, and why do we know this works? I never asked them to test it again. It feels like we've done it once, and that was kind of it. And I know they're not remembering it. I know they forget it. And I actually want them to remember this. I do want them to know this. So doing it this way around didn't seem like a very good way of helping them remember in the future, because of that choice I had to make about what we practice. In one way, practicing it, the full working would be rejected even if I went for it. And I go with the other way, they're guaranteed to forget it. Is there anything in this that I haven't said? Not a great deal. I suppose bullet point number 2, if I opt to go straight into let's ignore all that and just add the indices together, I think it just makes the whole experience frustrating. So why did you bother? Why did you make this so confusing? Final problem with this, which is the one that I think in some ways, I think the others are more concrete, but this is the one that always, remembering this experience myself in the maths classroom, and actually seeing it when I've observed other people teaching, I feel it on behalf of the students. It's like we're giving them a point A. We're saying, I want to, here's an expression that you're familiar with. There's these two numbers in index form. We're going to multiply together. I'm going to show you how to simplify it. And then given that starting point, we then set off on this painfully long journey where we don't really know what the end point is going to be. We don't know how long it's going to take for us to get there. We end up getting increasingly frustrated. I would get frustrated with my own teacher. I feel like my kids have gotten really frustrated with me as I go through all of this, just kind of just wanting it to end, feeling like this is some kind of punishment. Until it creates this image in the back of my mind of like kids in the back of a car on a journey going somewhere, and they don't really know where they're going. They don't know how long it's going to take, and you're an hour in, and already they're crying out, "God, are we nearly there yet? How much longer?" I remember being that kid. I remember being that kid in the back of the car as well, and experiencing that frustration, even just on a 2-hour car journey. It's not a pleasant experience, and that's what it makes me. That's what it feels like. Whenever I've tried teaching this way, it feels like the reaction I get is, "Why are we doing this? When will it stop?" And no matter what the context is, it's not just index numbers, it's anything I've done, like showing where the formula for deriving the formula for the areas of different 2D polygons from first principles, rather than just giving them the formula. For me, this is really beautiful and interesting and fascinating. And I was never taught it. So I'm so excited to teach this to the kids, because when I saw it, I was amazed to see how simple it was and how beautiful and elegant it was. And the reaction I get is as if we've been on this long car journey and we've turned up in Dullsville, and they're even more frustrated and angry with me because, so what was the point of all that? And I feel like this is the solution. The solution to all of this is presented if we simply teach the what before the why. Going back to the example I shared, I honed in on just a single thing. There's only one thing I asked them to do. And even when I took them on this extraordinary expansion sequence, I changed one thing each time, or I just changed one thing that they had to think about compared to what they'd had previously. And it dramatically manages the cognitive load compared to what we've seen before. So we've now got an extremely high signal to noise ratio. It's very clear what I want you to learn and how. Very unlikely to experience cognitive overload. And therefore, because of the extremely high volume of questions I'm able to ask in the same period of time, very likely to recall this fluently in the future, which is going to free up even more of your working memory in order to think about the more advanced things I want us to get into. When we come to this more extended practice, whether it's the expansion sequence or when I eventually come to explaining the why, again, in every case, we're either practicing exactly what I just taught in the initial assessment sequence, or we're using questions to expand the initial concept enormously. And then we can choose to practice the why independently of correctly performing a simplification. So instead of trying to learn all those different things all at once, now you already know how to simplify. You're a master of simplifying numbers in index form. We've been doing this for days. Now we just get to focus all of our attention on this issue of why. And it's being said quite a bit now. I know Peps McCrea mentioned it in his book. It was mentioned in one of the workshops earlier today. I think Daisy Christodoulou first came up with the idea that attention is the currency of learning, and it's coming out of social media and advertisement battlegrounds where everyone's really fighting for attention these days, fighting for eyeballs. We now have all of their attention on the why. When we did it the other way around, we didn't have that. Now we do, and that is so powerful, and it manages cognitive load. And then finally, this issue of the unending journey and where are we going and what's the point? Well, now we know where we're starting and we know where we're going and we know what the point is. Oh yeah, I don't know why this works. Does it really work? I have just taken your word for it. No, I want to know why it works. And now it's a much more straightforward journey. We know where we're going. We know what the endpoint is. There's much less to process. I've mentioned that attention can be directed directly just to this new link between them. I've said, again, there's a clear purpose to what we're doing to understand why something that was previously mysterious to us suddenly works. And you know what? The end point is not Dullsville anymore. This is now a satisfying aha moment. Something that previously eluded me now makes sense. I get it. I can see why that works. We were forever wondering how we get that same feeling we experience when I was shown how these things work, when I was shown the proofs for the area formulae. Yes, I was excited by them. Yes, it was a big aha moment for me, but I knew the formulae inside and out to begin with. And then I was trying to show them that proof before they'd even knew the formulae and been comfortable with them and been using them, and wondering why they weren't experiencing the same joy and satisfaction that I did. And now I'm convinced that this is the reason why. I said I'd give one more concrete example, and so I will. This one is for solving quadratic equations. So the way I used to do it was to start with a quadratic equation, quite often this one, invariably a is equal to 1, so we have 1x squared. Then ask the kids to factorize it, like so, and then it's, we do something, either I would explain or I'd make the point. We can treat these effectively as two numbers that multiply to make 0. And so one of these two brackets must equal what, must have a value of what, if they're going to multiply to make 0. Talk to your partner. Okay, one way or another, we've come to the conclusion that either A or B is 0. So if A is 0, then that means x plus 3 is 0, which means x is equal to -3, and we have our first solution. If B is 0, that means x plus 2 is 0, which means x is equal to -2. We found our second solution. Like before, I would probably go through 2 or 3 versions of this, and then I would reach out to the internet to find some sort of practice worksheet to now just start going through. It's not how I do it anymore. It never worked. I never had much success doing it that way. The way I do it now, I actually start with, I'll start with something like this. So I don't start with x squared plus something. I don't start with it in a squared plus b plus ax squared plus bx plus c equals 0 form. I start with it in factorized form. I think some people in the workshop, I'm certain some people in the workshop do this themselves already. If you don't already do this and you're curious as to why, I can't quite go into it right now because it's part of a bigger thing. It's to do with atomization and concept chaining. Coincidentally, since I signed up to do this, I'm now doing another webinar on Thursday, which is sponsored by my company, so it's free. And I'll put a link up so you can join that one if you want to know more about atomization and concept chaining. But suffice it to say for now, this is my starting point. So I'm starting with this. We may have some, they know that we're going to learn to solve quadratic equations. We will have done something previously so that they identify this, they recognize this as being a quadratic that's just in factorized form. And then all I'm going to say is that for this equation, there are two solutions. To find the first solution, look at the first bracket, flip the sign and put it over this number, flip the sign and put it over this number to get the two solutions. And I'll point to the numbers, of course, because I'll have a whiteboard and I'll be in a classroom, but I will literally do that. I will say you flip the sign, you put it over that number, you flip the sign, you put it over that number. I'm very careful to put the minus sign for the second solution on top of the fraction rather than to the left of it, because I want it to be associated, the -2, I want it to be associated with the +2. Now remember, this is my starting point. I think there's like a whole wave of maths teacher CPD that would argue exactly the opposite of this. So this is bad. This is how people have done it in the past and we should not be doing it. This is my starting point. It's my starting point because once again, I can go back to my year 7 bottom set and they can do this and they can do this with guaranteed success. They will not fail. They will absolutely not fail. And then I will change just one thing. In this case, I'm going to change the 4 to a 7. And then I'm going to show them how that changes my first solution. I'm then going to change just one thing. I'm going to write a 1 in front of the 3. I get 13x, and I'm going to show them how that changes my second solution. And I'm then going to hand over to them. It's your turn now, mini whiteboards. Give me the solutions to these two. Sorry, give me the two solutions to this equation. From that point onwards, we'll change just one thing, the 7 to a 10. I'll change the 4 to a 6. At this point, I need to make another really important point. The solution I'm looking for here is 6/3. I do not want 2. In other words, I do not want them to simplify it. If a pupil were to simplify it, I'd be perfectly happy with that. I'd tell them they have it correct because they do. And in fact, they're doing a bit more. They're doing a bit more mental work there. But I'm not going to ask for it at this stage. This is such an important point. Again, it relates to managing cognitive load. Again, it relates to atomization and concept chaining. Again, I will put the link up to the other webinar in a bit. So if you want to learn more about that, you can do that there because I make this point in that webinar a bit more clearly. I go talk a little bit more about it and why it's so important not to insist on simplifying at this point, which again, I think is a little counterintuitive. And now I'll change one thing. I'm going to change +11 to -11. And then I'm going to change one thing again. I'm going to write a 7 and a 1 in front of that 3. So we've got 713x. Again, it's one of those tricks that you can do with certain groups that makes them feel very smart, very successful, gives them a real sense of success. There are some other interesting things that could be done with this, either in initial assessment or in the expansion sequence. An obvious one is, two obvious ones, in fact, are having a negative x term. And another obvious one is flipping the terms around. So you have something like 6 plus 3x instead of 3x plus 6. I would do that depending upon the group. I would make a judgment call as to whether or not I would need to demonstrate it once first as part of initial instruction, maybe a new sequence after we practice this, or whether I would hand it over to them in an expansion sequence. It depends. Each time I'm making a judgment about what I think the group can do. And I'm looking for as close to 100% success as I can get. If I think they can do it without me showing it to them, I will let them do it without me showing it to them. That is always preferable. This is a little different from the last one because this is a much more, ultimately solving a quadratic is a much more complex exercise than simplifying numbers in index form. So it involves an initial process of atomization, and then for each atom, there's initial instruction, assessment, expansion sequences. Those things would loop around until we would then have this process of concept chaining. So this would go on probably for a lot longer than it did with the numbers in index form. I would spread it out for as long as I could. I did this with a mixed attainment year 9 group when I was at King Solomon Academy, and I expressly told them, I am not going to tell you why this works. I am not going to tell you why flipping the sign and putting it over this number gives you the solution yet. I promise I will tell you why this works in the future, but I'm not going to do it now. And for the rest of that week, I had the kids in that class putting their hands up when I asked them any questions, and them asking me, so, but why does it work? So that meant that when I came to the lesson, when I was now ready, when I was now convinced that they knew how to do it, and I was ready to teach them why, I now had a class of kids who've been asking me all week why this works. I had all the attention that I wanted before going into what is a slightly difficult thing to understand. I probably, for this one, because actually there is some abstraction going on, I wouldn't, the slide I've put at the bottom of this, showing the why, that's not actually how I would do it. For this, I would again do a bigger process of atomization and building little bits and pieces up to make sense out of it. Because when I've tried, even when I've tried it this way around, after going through all of that initial what, I had all the attention, but I still lost more than half of the class, which isn't good enough. So the way I would actually do this is a bit different from that. There's ways of breaking it down so that you guarantee they know each bit of it. I just haven't put it in this presentation, for which I apologize. Okay, so just brief aside, if you want to learn more about the concept chaining, the atomization and stuff, I basically shared a tweet a couple of days ago that has the banner for the session and has the sign-up form in it. Because it's sponsored by my company, it is a free webinar. It's on Thursday at 11. So I'll give you 15 seconds to just read that. And even if you're not on Twitter, you can easily find this by just going to Google and typing my Twitter name, which is at the top there, Chris_Boulton. Twitter, you literally just type that and Twitter into Google, and it'll come up with my Twitter feed. And I haven't tweeted loads recently, so it's one of my tweets from the past couple of days. And then at the bottom, there's a form to sign up for it. Okay, so that is what I'm calling part 1. Now, this last bit of commentary on this, these last 4 points. Why I didn't do it from the start. 3 points. First of all, I conflated understanding with recall. I believe that if you understand something, then you never forget it. That is entirely incorrect. It's incorrect based on cognitive theory, cognitive science. It is incorrect based on my own experience, and I'll share one momentarily. I conflated input with output. I looked at the end goal and I assumed that the starting point needed to look exactly like the end point. And that is incorrect. And I'll look at what helped me overcome that, because that was a big one for me. Also, Skemp was mentioned in the first session I was in, Richard Skemp. There's some stuff he's done that I really like. What I'm not a big fan of is a paper he's particularly famous for, published in the 80s, where he coined these 2 concepts of understanding, relational and instrumental. And part of what he says, and it was a big part of my teacher training, and part of what he said he did was he was interviewing teachers. And one of the questions he'd pose to teachers is, how do you know, do you think your kids understand this? And they'll say yes or no. And they'll say, how do you know they understand it? And then some of them would say, well, look, they're getting all the answers right. So clearly they understand it. And other teachers would say something about how they understood the relationship between various different concepts that they'd been talking through. And so he felt that within teachers, there were 2 groups of teachers, some who thought instrumentally. They thought about understanding in terms of getting answers to questions, and the others thought relationally. They thought about it in terms of understanding the connections between concepts. And he sets up at this point, I think, that part's all fine, but then I think he sets up a false dichotomy. He starts talking about relational teaching versus instrumental teaching. And he starts arguing that you need to teach relationally. In other words, teach all that complex understanding right from the beginning, rather than focus on getting some things right, to some very basic stuff first of all, and building up from there. So I think that was a false dichotomy. What helped me overcome it? One, I mentioned my own experience. I have seen the proof that the square root of 2 is irrational about a dozen times now. I've taught it once for some reason, largely because I've never spent much time trying to recall it from memory. I can't remember it. I'd recognize it if I saw it very quickly. I understand it perfectly. I just can't retrieve it from memory. I need to look it up every time. Also, I mentioned that year 9 mixed attainment group I taught. They were put into streams when they were put in year 10 and 11, so a top, middle, and bottom stream. And I taught them in year 10 and year 11 as well. And in year 11, I did a small unit on proof with them over a few lessons, including geometric proofs. And I took this opportunity to very excitedly teach them, to basically practice what I preach. I taught them why all of those formulae for the areas of shapes they'd learned and used for years, why they worked, where they came from. And I got to the end of one of these, I think it was the trapezium. And one of the girls in the class, when I got to the end, suddenly called out and noted that they'd been taught this by Mr. Reddy in year 7. She said, oh, I remember Mr. Reddy teaching us this in year 7. Now that moment is interesting. It's interesting because she could not retrieve from memory the proof for the formula for the area of a trapezium. She did not know when I presented this in the beginning that we were going to cover it, that she'd learned it previously. Once she'd seen the whole thing, she did finally recognize it, but not until she'd seen the whole thing again for probably the first time in 5 years. That was interesting. The second thing that was interesting is that the rest of the class looked at her with a basic expression, and some of them saying out loud again, what, did we? Because they were all in the same class. They were taught by the same teacher. So Bruno had basically done the why before what thing that we were all being told was the right thing to do. Had gone through explaining where these came from, derived them from first principles, didn't just give them a formula and ask them to accept it. But then that was their only experience of that proof for 5 years, and they all completely forgot it, barring one girl who just about recognized it when I showed them the whole thing again.
I'm not sure.
So that wasn't the way. If we're serious about this, if we really want students to understand these things and remember where they come from and recognize the proofs, that isn't the way to do it. Going through the why once and deriving the formula from first principles, that is not the way to do it. I think the way to do it is obviously how I've shared it today. And ultimately that is a beautiful starting point as well for anybody. I was in a school 6 months ago. I talked about this on a podcast with Craig Barton recently, and there was a girl in a class of bottom set year 8 group, a class of about 18, blasting through questions on an online platform. And she wasn't getting any of them right. And I saw her get unable to even expand a very, very simple single bracket. And in about a minute, I'd gone through a simple instructional sequence like the one I shared. I didn't even tell her you need to multiply, what they need to multiply things together. I just talked her through I just showed her a sequence. And she was then able to expand several more brackets that I gave her herself. So it's just fail-proof. It guarantees success for every student for their initial experience of any new topic. I strongly recommend looking up Dan Willingham's idea of flexible knowledge. He is what helped me overcome this dichotomy view of understanding. You either have it or you don't. He instead builds up a continuum model. You start with very inflexible knowledge, which you, over time, build on more bits and pieces until it becomes very flexible. You've got many relationships between the bits of knowledge that you have, and you're able to apply them in a great many more contexts. So he helped to explain the idea that it's not one or the other. It's like what we're doing, you're building it up bit by bit. And then ultimately cognitive load theory, which I imagine many people are now familiar with and I've referred to a bit throughout. But also Siegfried Engelmann's approach to teaching cognitive routines. That's where a lot of these ideas are originally adapted from. So that was another, and a lot of his research was empirical, it was field research. He tried new things out until he found what worked. Quickly, what this isn't, it is not meaningless. Dividing two fractions, I am actually quite comfortable with the flip and multiply to divide two fractions as a starting point. As a starting point, I'm very happy with ours is not a reason why, just invert and multiply for now, and then I will later actually reason why. That's how I would say, because otherwise, again, all the problems, imagine trying to, it's so difficult to grasp in the first instance. All the problems I've talked about manifest if you start with the why, whereas flip and multiply as a starting point is very, very straightforward. But I would insist that the word fraction is meaningful and that division is meaningful. If we're finding solutions to quadratic equations, I want equations to be a meaningful term to you. I want you to have that concept. I want you to have the concept of quadratic equations. I want you to know what a solution to an equation is. We are not going to just write down meaningless numbers on the page. You need to know that the number you have at the end, even if you don't yet understand why it's a solution, I want you to recognize that it is a solution and you know what it means for it to be a solution. So unendingly important that all words, concepts, are meaningful. We know what we're doing and we know why we're doing it. We know why we're doing it. We just don't know yet why it works. And it is not what without why. It is what before why. Finally, what is still missing? This on its own isn't enough to develop mathematical reasoning and behaviors in all its glory. If you want, I don't know how far we can take our expectation for school mathematics around things like developing investigative ability, mathematical investigative ability and mathematical problem solving ability. Obviously, I would like to take it as far as we can. I don't have a clear sense of what the limit is with the time we have available to us. But sometimes I feel like people hear me talk about things like this and they think I'm entirely opposed to activities like that. Rather, I see this as a foundation. We have to do this first and then build on it. So you could look at the foundation of a house and say, well, that's no good. You can't live in that. And that's absolutely true. But you're not going to get the house until the foundation is at least been built. And I don't go in for trying to teach substantive content through investigation. For example, I would never go for teaching Pythagoras' theorem through an investigation or teaching what pi is through an investigation. It's what I call a have your cake and eat it approach, trying to use the time available to teach two things simultaneously, investigative inquiry skill, problem solving, whilst at the same time teaching the substantive facts, concepts, processes that we want kids to learn. I feel like it leads to all of the problems I've already talked about. We need to isolate distinctly the what and the why, teach them distinctly, engage in retrieval practice distinctly, and then obviously connect them together. But we need to treat our teaching of them as separate things, not pretend that we can get everything that we want out of this all in one go. The same, I think, goes for inquiry, problem solving, and so forth. You can better to do an investigation where we don't care about the outcome. One, we are just engaging in the investigation for an investigation's sake, just to attend to what it is to conduct a mathematical investigation, what it looks like, what it feels like, to get a sense of what it's like to be a professional mathematician, rather than worrying about what the output is at the end of it. I think there's probably no time for questions after all that. Contact detail at the end. I'm going to try and see if I can get back to Zoom and the Q&A. There are 23 questions. I don't know if they're all from they are all from my talk. There's one in the last hour.
You've got a couple of minutes, Chris. You can use to answer some questions if you wish.
Great. Well, there's a couple that have a huge number of thumbs up compared to the rest, so I'll take a look at those. How would you approach something more complex like adding fractions with different denominators? I've honestly got to suggest coming to the webinar on Thursday, because the more complex something becomes, the more likely it is it's what's called a cognitive routine, the more it falls into the domain of atomization and concept chaining. And even what I'd say about that is going to be relatively brief. I could do a day on it. I'm probably going to do 30, 40 minutes. But I'm definitely going to do more about it on Thursday than I had time to do today. But suffice it to say, you need to atomize, you need to treat each atom independently, you need to teach each atom independently, you need to know how to chain it together in ways that are effective. My initial example is pattern spotting. So can I understand this? They're constructing the idea and then they're just giving it a name description, which is almost arbitrary. how does this work for more complex concepts, not just fact-based, such as solving equations. I think the first part that you said, Catherine, is entirely correct. There is a pattern spotting process at work. And then you're right, the names often are arbitrary. And again, the second session I was in, I'm sorry, I didn't pick, I can't remember if it was David Busby, that was who the second session was. He talked about mix the tricks and things that are fundamental and things that are arbitrary. Yet labels and naming very often are arbitrary. And I always give names after I've explained how to do something in more simple forms. Again, how to do it for more complex concepts like solving equations. That is, again, it's a cognitive routine, it's atomization, it's concept chaining.